Hello everyone, my name is Thilo and I feel honored to be able to speak to you here today and to explain our research in the field of additive manufacturing in structural engineering. I created this presentation under the leadership of Professor Lange and together with Benedikt Waldschmidt, and the subtitle is Steel Fabrication with Wire Arc Additive Manufacturing Using Difficult Positions and Non-Neutral Torch Orientations. Now you can see a time-lapse video of how an arc is made using the type of additive manufacturing we use. The WAAM method is called Wire Arc Additive Manufacturing. I will explain this method in a bit, but what I want you to know now is that it's based on welding and the arc consists of punctual welds. As you can see, it's possible to print mid-air, but also the quality or the geometric stability of the welds get worse the more we print sideways. So my presentation will be about the challenges of printing in difficult positions, which means the welding torch prints from the side and partly overhead. And if there are geometric constraints, for example like this, and the welding torch would collide, the torch has to be rotated, and this means its direction differs from the manufacturing direction, which makes it even more difficult. So this is the agenda for my presentation. First, I want to briefly introduce you to the wire arc additive manufacturing process. Then there is the question of what should we print with steel in structural engineering. I would also like to show you a few selected examples and, so to say, the business case for wire arc additive manufacturing in the construction industry. You will see it is necessary to print in difficult positions, so in this step I will focus on this task and explain. I also want to show you two bridges that were printed with the wire arc additive manufacturing. And before I sum up the presentation and give a conclusion, I will share the results from an investigation where we found out how to increase the deposition rates, which is one of the main goals in additive manufacturing. Now I want to start with explaining the wire arc additive manufacturing. The WAAM process we use is called, and I maybe mentioned this before, wire arc additive manufacturing, or WAAM, or just WAAM. Here you can see the welding torch of a welding robot. And the welding robot works with normal gas-shielded metal arc welding. The wire electrode here is the printing material. And with this we can achieve deposition rates up to 5 kilograms per hour and more. This is a common WAAM setup, which consists of a robot and a welding machine. For welding, you need, of course, wire and gas, and the whole setup is operated by the controller. Now, all you need is, for example, a base plate or a beam to print on. As you can see, this is not a special or expensive setup. You can easily get welding robots. Such systems are much cheaper than powder-based systems, not to mention the difference in material cost for powder on one hand and wire on the other hand. Wire is much cheaper. Now I would like to move on to what you can print useful. When you think of steel construction and consider what can be manufactured additively, you certainly don't think of rolled beams and large sheets. No, their production is already highly optimized. Even if we can print steel at high deposition rates, as I mentioned before, we'd better focus on small elements, such as connection elements like stiffeners, plates, etc. First, their mass is very small and printing is quite fast. Secondly, their assembly in the factory takes 60% of the time. That's where the costs are, also because this work is done by hand. What if we could print these elements directly onto the beams? Now you might say, should a steel constructor buy himself a welding robot? And here we say, yes, why not? There are already automated production systems. Here on the left we see the steel beam assembler from Siemens. and on the right the fabricator of the company Feucht. With the help of a handling robot, the system automatically picks up sheets and connection elements, for example head plates, stiffeners. The handling robot holds the elements to the steel beam and the welding robot automatically welds them on. So there are already automated production systems that work with robots and welding robots. It is easy to integrate the additive manufacturing there. With all these systems, you have to keep in mind that you always have to have plates in stock in different thicknesses. The keyword here is material disposition. The plates must be cut to size and drilled, and this always leaves a waste that has to be temporarily stored or disposed of. The logistics behind this cannot be ignored either. The plates must be delivered to the installation site in good time. These steps are necessary in every conventional steel construction production. In automated production, the plates must be also scanned or measured to check tolerances. However, if the connection elements are applied directly to the beam with the aid of additive manufacturing, all these steps are no longer required. The only things you need are shielding gas and wire electrode. So now when we have the business case, we can move on to some examples that we investigate and that we print. Let's take a look at a conventional I-beam, simply supported and carrying a line load. Typically, such beams tend to lateral torsional buckling, which means the beam tends to rotate and warp sideways. In red you can see stiffeners above the support, and these stiffeners have two main tasks. The load introduction of the shear force from the web into the support and preventing the profile from deformation at the support, which strengthens the ultimate load of the beam against lateral torsional buckling. So we have two tasks for the stiffeners, and now we optimize the shape of the stiffeners, particularly for these two tasks. First, the load introduction, which leads to this partial stiffener, and preventing the deformation, which leads to these two rod-shaped bracings. A short throw in, we use topology optimization to find these structures. Now the question is, would anybody manufacture these shapes out of a plate? Would anybody cut out the holes in these plates? Of course not. So this is the perfect application for additive manufacturing, combining topology optimization and additive manufacturing. This marriage produces wonderful kits. For the first application, I want to show you the manufacturing strategy with the wire arc additive manufacturing. The I-beam is rotated 90 degrees, and if we want to print the stiffener with a neutral torch orientation, the torch would collide with the flange, and there would be an insufficient connection between the additively manufactured stiffener and the flange. So the torch has to be rotated when printing the area near the flange. When the torch prints the layer, it has to be rotated back to the neutral position, as otherwise it would collide with the other flange. Now, the rest of the stiffener can be manufactured with these principles. But because of the thermal shrinkage of the additively manufactured steel, the flange would bend, what we want to avoid. And we tested this manufacturing strategy and it was not feasible. So that's why I would like to show you another manufacturing strategy. And in this strategy, there is a gap between the stiffener and the flange, so that the stiffener can shrink without affecting the flange. And afterwards, the gap is closed with separate welds. And now I want to show you a time-lapse video of the manufacturing of one partial stiffener for the load introduction. First, there are shown some still images to illustrate the rotation of the torch. By the way, in the back you can see our red robot Mario, who is leading the welding torch. And you can also see now the gap between the stiffener and the flange, which has to be closed afterwards and will be closed right now. Yeah, so this is how an additively manufactured stiffener in an I-beam looks like. The rotated torch leads to particularities which must be taken into account. Firstly, the forehand and backhand welding, which occurs here, affects the weld penetration or the remelting ratio. Forehand leads to more penetration and backhand to less penetration. So we have uneven conditions for each layer, especially in the area of the flange. Secondly, the layer height must be known exactly. For example, if the layer height is calculated too high, the wire will miss the interlayer. And with the neutral torch orientation, as you can see here on the right, you don't have this problem since it only affects the stick out, which has a very small influence on penetration. But especially in the area of the flange, when the layer height is wrong, you can miss the interlayer, and you have to be aware of this. Then we have the other application for a stiffener, namely to prevent the profile from deformation in the area of the stiffener. And for this purpose, you can print a rod-shaped bracing into the beam and connect the stiffener and the flange, while the flange otherwise would be free or not connected and the profile could bend. And here we have a similar problem as with the stiffener itself. If we want to orientate the torch in the direction of manufacturing, it would collide with the flange. So again, we have to rotate the torch. Let me show you a detail of the situation. Here you see each layer of the puncture welds we use to manufacture the bracing. In yellow we have the manufacturing direction, and in green the torch orientation. If the layer height delta Z, so the distance between the puncture welds, is not programmed accurate, the angle of the bracing would differ. So if delta Z is calculated too low, we would print more on top of the bracing would come out steeper and miss the flange, as you can see on the picture on the left. And if delta Z is given too high to the robot, the angle of the bracing would be less, as we would print more underneath or sideways to the bracing. It also could happen that the wire misses or the fluid steel would drip down. So to sum it up, the manufacturing direction and the torch orientation don't have the same angle. Then the layer height delta Z must be known exactly. And here we talk about up to 1/100th of a millimeter when manufacturing the whole bracing at once. I would like to introduce you to another element that is often used in steel fabrication and that can be welded directly onto a steel beam using additive manufacturing. These are clamping elements which are used to connect diagonal braces to a beam web. And these clamping elements consist of a form part and a curved piece. The form part, here in red, is welded onto the web in the factory by hand. A hole is drilled in the web through which the diagonal brace is inserted on site. Finally, the washer and the curved piece, here in gray, are put on and the nut is screwed on. The form part and the curved piece are castings and are made for a range of possible diagonal angles. So one element for a range of angles. If you optimize the topology of the clamping element, you can optimize it for a specific angle because it is manufactured individually for each particular case. Now you get a quite simple body, which can be seen here on the right, also in red. It is a cut pipe if you want, but the mass of the element is now much smaller compared to the cast steel elements on the left. The following video shows how this topology optimized clamping element can be manufactured. It is again a time-lapse video made at our institute. The element is separated into 3 segments, and on the right, the sections with the segment produced at the moment are displayed. And first we have full ellipses, then the ellipses are cut and get smaller, and in the end, to get a good surface for the washer and the nut, we have welded circles. By the way, the welding time for these elements range from 2 minutes to 5 minutes, depending on the angle and the diameter. So these are manufactured really fast. Now, as I mentioned earlier, the elements can be printed for different angles. We tested angles between 60 degrees and 37 degrees, with 60 degrees having almost a neutral torch orientation to the ground and 37 being more cantilevered. We stated before that it's more difficult to manufacture when the torch orientation differs from the manufacturing direction. But with all the experience we made at our institute, we can say torch orientations below 45 degrees are not suitable. So the 37-degree element on the right, we would suggest to manufacture with a torch orientation of 45 degrees. One reason is the gas nozzle could collide with the surface at the first layer when having 37 degrees torch angle. And the other reason I want to explain in the drawing on the next slide. I showed a similar drawing a few slides ago. Now, when the wire hits the interlayer, the drop is affected by the arc pressure and the gravity. And if the torch orientation becomes lower, the angle between gravity and arc pressure increases, and the two forces disturb each other more and more. They cause the liquid drop to become more turbulent, and then the drop tends to drip down and tends to become less smooth. The other thing is we attach the drop a bit higher or more on top of the interlayer, and then it can cling better around the interlayer while hardening. Let me summarize what we learned so far from our research. If the torch orientation and the manufacturing direction are different, the layer height delta Z must be known exactly. And secondly, a torch orientation smaller than 45 degrees should not be used. So these are the two main findings I want to point out right now. In the examples I have shown you, you could see that we can print cantilevered structures nearly mid-air, what opens up completely new possibilities of structures that can be manufactured. And therefore, I want to present you two bridges of steel that were printed with the wire arc additive manufacturing. I want to start with the project of MX3D. They are a startup from Amsterdam in the Netherlands, and they have shown what can be done with 3D printing in the construction industry. They built a complete bridge with a span of 12.5 meters with the WAAM. And as you can see, structures with great geometric freedom can be realized. By the way, this picture is from the opening in July. What they did was to manufacture segments of the bridge in flat position. There is a base plate, and then they manufacture vertically. And afterwards, they rotated the segments and then connected them with manual welds, as you can see here. So all the videos you can see in the internet of the robot printing sideways onto the MX3D bridge have been created for show purposes only. Nevertheless, a fantastic project which gains a lot of publicity for the wire arc additive manufacturing. So this was the first project I wanted to show you related to printed steel bridges. And now I want to introduce you to the other printed bridge. The project is called AM Bridge, and we had the idea in the end of 2018. When we started our project, we had in mind to print a bridge over a small creek in Darmstadt, the city of our university. We said, let's put two steel plates on each shore, let's put a robot on one shore, and then let's print a bridge of steel. And yes, we wanted to print a bridge directly on site, without scaffolding, without assembling, only with a robot. And we knew this will be not an easy project, and I want to show you why. On the left you can see the common and the easy way to manufacture additively. In flat position, just straight upwards. So far so good. But what we wanted is to print over something, as you can see on the right. We need to print cantilevered structures, but there is always the risk of weld metal dripping down. So that was the main problem to solve. And We made it, and the following welding process, which now I want to present you, was the key and makes it possible to print cantilevered structures without weld metal dripping down. The process is called CMT cycle step and can be executed with a Fronius welding machine. Look at the following video and listen closely, then it becomes clear what the special feature is. So there is a short welding time with a certain number of CMT cycles or ignitions, and a short pause time with a defined length. And welding then starts again. So we have welding time, pause time, welding time, pause time, welding pause, and so on and so on. So this might be a simple trick, but a very effective one. And the advantages are the less energy input, which is important in wire arc additive manufacturing, and the controlled solidification of the melt. We tested the process in this manufacturing experiment where we manufactured a 1:8 scale model of the bridge. Again, a time-lapse video. And after we saw that the manufacturing strategy and the welding process works, we said, okay, now let's start and print a bridge on site. And this is a picture from the construction site. As you can see, we needed a pond and a tent, there are the steel plates also. By the way, the foundation for the steel plates was made by Spinanker, an Austrian company, and the foundation is a concrete-less foundation and is built very quickly. And the next picture was made after a few days. The bridge took shape. Here is a video from the construction site while the bridge was manufactured to give you an impression of the construction site. So when you go home after a long day on site and lay on your bed, you can imagine what kind of sound you have in your ears. And in the beginning of November 2019, we finally closed both sides of the bridge with a stripe in the middle of the bridge. And that was a great experience because it was the moment we worked hard for so long, and there were some TV stations on site also, and unfortunately a few days after that we had to leave the site and get out the bridge because in this place now stands a new building. And yeah, here are some impressions from the site after the tent was removed. As far as we know, this is the first bridge ever printed on site over a flowing water. And maybe this is a look into the future. I don't know. We don't know. I'm curious to find out what your ideas and thoughts are. But what we can say is that it is possible to print a bridge from steel over flowing water. So this is the last point of my presentation. We made an investigation on how to increase the deposition rates of cantilevered WAAM structures. And therefore we tested different mixtures of shielding gas. I personally didn't expect the gas mixture to have such a big influence, but actually it has. We have these three gases which are often used in wire arc additive manufacturing. We have argon, carbon dioxide and oxygen, while carbon dioxide and oxygen are active gases and they react with the weld. These are the three mixtures we tested, and the main difference between them is the amount of carbon dioxide. The wire we used was an AWS A5.18 with a higher ratio of silicon and manganese. The welding machine was a Fronius TPS CMT advanced machine, and we tested these two manufacturing directions, 45 degrees and what is really challenging, 90 degrees, which is horizontal. And the torch orientation, of course, was constantly at 45 degrees. Yeah, and these are the results. We were able to increase the wire feed speed up to 7.5 meters per minute with the gas Ferroline C6X1, which results in a deposition rate of 1.65 kilograms per hour, which is 8% higher than with the C18. By the way, for the bridge, we used the C18 and an AWS A5.18 wire without higher silicon and manganese ratios and had around 1.1 kilograms per hour deposition rate. So the deposition rates we now can achieve are 50% higher. And I don't want to bore you with details in material testings, but we conducted notch impact tests and tensile tests, and they have shown good results with sufficient properties. And what I can say also is that the process stability and the surface smoothness was absolutely the best with the Ferroline C6X1, which has 6% carbon dioxide and 1.5% oxygen, and the rest is argon. So let me sum up my presentation and mark out the main results. We found out that connection elements are suitable for additive manufacturing in steel construction, because usually assembly takes 60% of the production time in the factory, and with our method you only need wire and gas and the robot makes the rest. We saw that difficult positions and non-neutral torch orientations are necessary to manufacture these connection elements. And we can conclude that if the torch orientation and the manufacturing direction are different, the layer height delta Z must be known exactly. We suggest that torch orientations smaller than 45 degrees should not be used, and if you want to achieve high deposition rates when manufacturing cantilevered structures, you should use Ferroline C6X1 gas and a wire with higher silicon and manganese ratios. We are supported in our research by these companies here, whom I would like to thank warmly. And this brings me to the end of my presentation. Thank you very much for your attention. I would love to hear your feedback, and I would love to see you in LA in the beginning of November. Until then, thank you very much again, and yeah, bye-bye.